Hi there. Today I'd like to talk to you about local variables on the stack in an x86-64 assembly program written in YASM. If you don't understand assembly or local variables or other things like that, you might want to see my other videos. But I'm just going to give you a quick example. So what am I talking about with local variables on the stack? For starters, forget what you're seeing here for a second. I'm going to open up a little blank code page and pretend that we're coding in C++ just for a moment. This is an assembly video, but pretend this is C++. So suppose you have C++, you have a main function here, and at the end of it, this is your entry point for your program. We return 0, and maybe above it, there's a function called f. I'm putting it above because I don't want to use prototypes in this video, but you should probably use prototypes. Maybe main calls on f, and so then inside of f, what happens? I don't know, maybe we have some arguments. We'll call this integer argument a that comes in. If you've watched my other videos, hopefully you have by now, you'll know that a comes into the function as RDI because that's the first integer argument register. But then when we start creating local variables, we'll say integer b equals, let's say, a 5, and then integer c is equal to an 8 for whatever reason. Maybe there will be an array, so I'll call this int array, I guess. We'll say that we have 100 integers in our array. We could also have a pointer, int pointer p, and then allocate it to some kind of new memory just to prove a point. And then, later in your function, you're probably going to want to do something with your data. So I don't know, maybe how about like b is plus equal to a, and then c plus plus, and then C++. C is plus equal to B for some reason. I'm just making random nonsense up, honestly. I'm just showing you that we use our variables. And then maybe you want to build an array. So we just declared the array up here on line 6, but maybe you want to actually do something with it. You want to fill it with data maybe. So I'll do size type I is 0, keep going until I is less than, as long as I is less than 100, I plus plus, and now I'm going through every single index of the array. Maybe I'll say the array at index I is equal to C, and then we'll just say C is plus equal to B, and then we'll do B plus plus, just to have something in there. Okay, so let me explain the parts of your program real fast. If you haven't watched my other videos, please do, because this should help a little bit. Anyway, so A is an incoming argument, like I said before. That's usually coming to you in the RDI register because it's the first integer argument. So we don't need to worry too much about that. We know that A is actually just a register in your CPU. And B, that's created on the stack. And C is created on the stack also. And the array is created on the stack. By the way, I could name the array anything if I wanted to, like just V. I'm using the name array because it's easier for me to say. But notice also that we have a pointer here. I just wanted to make a point that the pointers we make in our function are considered local variables, and that means they do sit on the stack, because what I'm trying to say is that local variables that are not arguments, they sit on the stack. But the memory we allocated and then gave to the pointer, that's sitting in the heap somewhere. So when you use the new operator or the malloc operator, or you're just like making dynamic memory, that dynamic memory sits in the heap, but the pointer itself, since we just declared it here, that sits on the stack. That means later on when your function ends, the p pointer itself will get cleaned up automatically, and itself won't be leaked memory. But if you forget to clean up your memory here, like I did, you'll have a memory leak. But I'm going to talk about memory leaks probably in some other videos somewhere else at another time. Anyway, so then we have our local variables here. Remember, B and C and array are all on the stack. And well, we just have our for loop here where we just kind of start modifying data. So why would we use the stack? Let me just do a quick tutorial. This is not a stack video. I'm going to make a stack video in the future, but I'll just do like a quick little rundown of what is the stack and why is it really good for function calls. Consider that sometimes f might want to call itself. Maybe it's a recursive function, or consider that there might be like a long chain of function calls, like f calls g and g calls h and h calls, whatever, and it just goes on and on and on. As long as it's not infinite recursion, like all the functions are calling themselves in one circle that never ends, you should be allowed to do that. We should be allowed to have a function f that sometimes calls itself or other functions, or maybe it's called multiple times within our giant call stack, our call graph. And this will work because these variables, A, B, and C, and array, are sitting on the stack, and the stack allows you to have sort of different instances of variables. So for example, and this is just a quick thing, this is not supposed to be a full stack tutorial here, but if we have like the function f, and let's say we call it at some point, maybe main calls f, and then let's pretend there's another function here. Main calls g, and then g calls f, and then f calls h, and then maybe h calls f. And did I write an h there? No, I think that's supposed to be a parenthesis. Sorry, I have bad penmanship. Oh God, it's even worse. Hang on, let me do another h here. I'll just do a g. How about that? F, g, and then what am I doing? Okay, and then g calls f again. Let's just pretend that we can have a call graph where f is sometimes called by something and sometimes calls something else, or maybe sometimes f is called by a different thing. So like, I guess this was supposed to be the g function, so maybe that's why down here was the h. Should I delete this video? I don't know. You know what? I'm gonna delete this this drawing and just do it again. Okay. Pretend we have f calls g, and then g calls h, and then h calls f, and then f calls I guess, and then eventually these functions start returning, right? Oops, how come my green's not working? Green, there we go. Too late now. So we can have like a really complicated call graph, and f might appear in there multiple times. And the point that I'm trying to make is each call to f along the call graph should have its own copy, unique copy of local variables. So the b for this first f call, let me just do an arrow here, we'll have a b, and you can imagine it as b subscript 1. And down here when f executes, you can imagine that it's got its own copy of b. So we can imagine this is b subscript 2. So these are two totally different b's. If you tried to use global variables for this, it would be really, really, really hard to get the code to work. And it would be really, really hard to debug. So that's kind of why we have local variables. The stack allows us to do this. So what is the stack itself? Again, this is not, a full tutorial on the stack, but I just want you to kind of see what's happening. Imagine a data structure that kind of grows upward. I'll say that here's the floor at the bottom, and when you put an item onto the stack, the items kind of stack on top of each other. So imagine that this is the call to f, and embedded within this little stack frame area, we'll call it a stack frame, but actually the stack continues to grow as you create and destroy local variables within a function call. We'll just imagine that there's, I don't know, a mini stack sitting inside of the stack that contains all the local variables. I'm not going to put a because a is an argument, so it's sitting in a register. But we could do, dude, I got to learn how to draw with this tablet. We got to do b and c and the array. I'll put AR for array, sitting in their own little spots on the stack within the major portion of the stack that is designated for that first f call. And then, maybe f calls g and some other stuff happens. I'll just pretend that a bunch of other stuff happened. And then eventually f is called again, but this is a different instance of the call to f. So that means it's got its own little area that is separate from the previous call to f. And again, we'll also have variables that we can create locally that are supposed to be separate from the original variables. Oh God, that's awful and ugly. I need to maybe decrease the size of my eraser or something. But imagine this is, these are two separate copies. So that's like what I said before, when we have like a B1 and a B2, basically. They're not going to be called B1 and B2, but they're just two separate instances. And I just want you to know. So then when we start returning from functions, like when this f eventually returns, and by the way, I know that what I'm drawing on the right doesn't match the code because this is not a function that calls itself, but just suppose that your code is a lot more complicated than what I drew up. When it eventually returns, all that happens is those items on the stack just sort of get not necessarily deallocated, but ignored. We'll just say that they're gone. They're still sitting as junk data in system RAM somewhere. And in assembly talk, we know that we have a stack pointer called RSP. We have a register called RSP that just sort of points to the location in the stack that is considered the top of the stack, like the most recent piece of data that we have available. So all the other data is actually still kind of above, but we're not pointing to it anymore, so we consider that it doesn't exist. So then when G eventually returns, you know, we just change the stack pointer, RSP, to point to that other piece of data. The G data frame and the other F data frame are still sitting above somewhere in memory, but we just ignore them, right? So that's how the stack works. And that's how we have local function call copies of all of our local variables. Something to note, this is not a stack video, but just something to note, that even though I draw the stack visually as growing vertically up, when you actually manipulate the stack in assembly, or just like in any language, the stack grows downward in terms of memory locations. So you can imagine, I'm trying so hard not to make this like a huge stack video. Imagine this is a memory location 80, we'll say. You would think that memory location 81 would be the next item of the stack, or I guess if you're considering the fact that the items on the stack are quad words, we would say it goes up to 88, but that's not true. It goes down to 72. So the memory location goes down, even though we imagine the stack growing upward vertically. Just so you know, that's the kind of thing we're going to do. So what I'm going to do is just show you an assembly program where we can create local variables. And I'm just going to show you how to create an array, because this array is just like a bunch of integers. And you can imagine it would be really easy to create only one integer by just imagining an example where the array is a size of 1. So keep that in mind. And I'm not going to show you malloc or anything like that. We're just going to look at the local variables. Okay, so for starters, I have a makefile here that's just going to compile a hybrid program. If you don't know makefiles or you don't know hybrid programs, that's okay. Just see my other videos. I've explained them in detail. The first source code file here is just driver.cpp. Again, this is a hybrid program, so I'm going to mix my C++ modules with my assembly modules, which is pretty cool. The whole point of the driver is just to contain the entry point, main. And I'm just going to print a hello message, and then I'm going to call the real function that I'm interested in, which I've named local_vars. And that's going to be all the assembly stuff that we talked about. I do an extern C block so that C++ can call an assembly module. That's explained in other videos. And then here's the real heart of what we got to do. Let's write up an assembly module that can do local variables. Okay, so again, if you don't know assembly, that's okay, but you need to watch my other videos before you can understand this one. So I'm going to just copy paste some starter code here. This is YASM assembly in x86-64. So I've got a data section up top, and I'm just going to define some messages. So, I've got like an intro message that just says, hello, I'm so-and-so. And that's not my name, but I like those kinds of names. And then over here, I'm going to do some printf formatted strings. That's why I'm using a hybrid program for this video. I don't want to import my own personal library. I want you to be able to do this at home with just the GCC libraries. So if we link a hybrid library, linking against GCC instead of linking against LD, again, if you don't know that stuff, check my other videos, then we're allowed to call C functions. In this case, we're going to call printf, and we're just going to give it the string %lu, meaning I would like you to print just, an unsigned long integer. So I'm going to give it a value at some point on the stack, representing a local variable. And then I want it to print as just like a long, like a string that a human can read. Then after that, this is the carriage return line feed, the CRLF. Printf won't flush its output unless that is sitting at the very end of the string. So I'm just going to use printf to also print my new lines. And then I'm going to null terminate the string so that printf doesn't freak out and try to print a bunch of stuff after the CRLF. And this was from another video. Let me get rid of that. We don't really need CRLF in this video because we're just putting it directly inside of the printf string. We're not making our own function to do that. So then I'm going to make some defines. I'm going to define that we're going to have 50 integers. So I'm calling this define 50. I'm calling it num integers, and I'm saying that it has a value of 50. So I want to make an array that has 50 integers. I don't know, maybe if you want to imagine 100, like the example that I just showed, I'm going to keep it at 50. And then we're going to define what is the integer size. So I'm going to use quad words, which are 64-bit integers. So I'm just going to say that there are 8 bytes per integer. That will help me multiply later. And then I'm going to decide to fill up the array on the stack with just some numbers, just to prove that I can, just to prove that we can manipulate and fetch the values of all this stuff going on in the stack. And I'm going to say that the starting value is 7. So when we're done with this, we should expect to see like an array of numbers that starts with 7, and it just kind of increases somehow. Then I'm going to do some system call codes. We talked about that in a different video. And then some file descriptors. I don't think we actually need anything but standard output, but I put it in there anyway. Then the next thing we're going to add is the text section. Let me just do copy paste on my solution here. So here's the text section, section text in YASM, and I'm going to let my module know that I want to be able to call printf, which is a function sitting in the GCC libraries. When I link against a GCC, I have the ability to do that. That way I don't have to come up with like a complicated printing method or use one of my own shared libraries or something. So we can just ask printf to do everything. So now here's the entry point for the module. It's just a function called local vars. I mark it as global, so it's accessible to outside modules, i.e. Or e.g. driver.cpp. And then so here's the label saying the function starts, and here's the return statement saying that we're done with the function. I'm not going to manipulate any registers inside of the function, so I don't really need to do any push pop to preserve them. First thing I'm going to do is call a welcome. Let me comment this part out, by the way. I'm going to call a welcome function, and the whole job of the welcome function is just to, print a welcome message to the user. So nothing that I haven't talked about before in other videos, so it's just we're using a system call to print a string. Okay, so with that in mind, let me open this up here and see if this is going to work. I just want to basically print the welcome message at this point. Clear and make run. And again, if you don't know makefiles or anything like that, see my other videos. So this is the driver, I think, that prints. Maybe I should change the driver's message to make it more clear. Hello. How about this is the driver, and my name is whatever. So I'm going to do it again. And now it says, hello, this is the driver. Okay, so that's the CPP module. And then here is the assembly module. And then finally the driver gets control back, and then the program exits. So nothing really happened. So now let's upgrade the assembly module a little bit. Next thing I want to add is the actual demo function, which is going to be absolutely huge. So first I'm going to start off with, how about just the signature here? Let's go right after the welcome module. And I'm just going to copy paste the signature, put a return at the end of it. So we'll consider this a function that can be called. And that means up here, I can just use that call demo instruction on line 47 of the entry point. And then now we have a demo function that is being called, but it does nothing. For starters, in my comments, I like to put the signature of the function, and I like to remind myself of how I'm using my registers. Hopefully I'm not using the same register in 2 different ways, but sometimes it happens. If it does, and I'm able to break my function up into multiple parts, I'll probably do it because that's easier to code, with modular thinking, modular programming. But in this case, I'm just using these registers. It's fine to use them. They are all designated per the ABI as callee saved. So that means the callee, which is the demo function, is responsible for preserving them. So if you don't remember that, or if you don't know about that, see my other videos. This is not an ABI video. So I'm just going to push all of them to make sure that they're preserved. I'm going to call this the Prologue. Then at the end of my function, I'm going to call this the Epilogue, where I just restore them in reverse order, because that's the way the stack returns data to you. The stack returns data to you in reverse order, so I have to pop in the reverse register order to unreverse the reversal, if that makes sense. Pop R13, pop R12. Okay, so I think 15, 14, 13. Okay. So I got that. Next thing we'll do is let's remember where the stack pointer started, because we have our register here that we're going to mess with. Let me just type RSP real fast. So this is the stack pointer register, RSP. This helps all programs know where they're looking at in the stack. All of your functions have to be really, really careful about messing with the stack pointer. If you do it wrong, you will crash the entire program, because not only will your local function not really know where its local variables end and begin, it probably also won't be able to remember its return address when you try to return from the function, because that is also sitting on the stack. And even if you were lucky enough to be able to jump back correctly to whoever called you, if you messed up the stack pointer, then you've also messed it up for any caller of you and any of their callers. So the whole program is ruined. So we'll start off by trying to remember where the stack pointer was. We'll move the stack pointer into the base pointer. All right, there's something that I didn't do here that I want to do. We should, since we're messing with the base pointer and other programs, other functions or modules might also rely on the base pointer and it's considered callee saved, we probably also want to preserve that too. So I'm going to do push RBP to basically say, I would like to restore, or I would like to preserve the base pointer so I don't mess it up for my callers. So that means I have to restore it with the pop, so RBP. The base pointer isn't necessarily a pointer to the stack, but it's often used as kind of like a bookmark. So we have RBP at the front and the back there. Let's see. Next thing I want to add is, so now that we've restored it, we're allowed to just overwrite it because, you know, we're kind of like keeping its value at the top. Then we're restoring its value at the bottom, and that means we can actually mess it up in the middle if we want to, and it'll be fine. Let me show you real fast what happens. What happens is nothing. The program is still okay because we restored it. So now we're using the base pointer to remember where the stack was. Now we've got to sort of calculate how much room we want to make on the stack. Let me show you what I'm talking about here. Remember, all of our local variables are going to be on the stack. And before we drew this thing where it was like, well, we've got like a stack sitting here, and let's just pretend that there's some kind of data sitting on the stack. Data, 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 right? If the stack pointer, dude, green, there we go. Oh, I erased my green. RSP. If the stack pointer is currently pointing to this frame, then in order for us to make room on the stack to hold our array, well, if the whole array is going to be sitting on the stack, that just basically means, let's suppose that we have 5 integers. Suppose 5. Suppose that we want to make 5 integers on the stack. That just means we need to do 5 extra slots. Let me draw it in red here. Well, let's see, can we get a green? No, how about a yellow? How about green? My green is just having a hard time. We can do it in red, even though this is not a bad thing to do. So I'll just draw like 5 extra frames on top of the stack here. 5 extra pieces of data. You can imagine these are all 64-bit integers, and so they take 8 bytes on the stack. Even though in our previous example we were using just regular ints, which are 32, we'll just say we're going to make 5 64-bit integers because that's easier, so they're quad words. So every frame is actually 8 bytes and not just 4 bytes, and it's definitely not 1 byte. So we make 5 of those. How do we make 5 slots? It's pretty easy. We literally just move the stack pointer. Let's see. We just move the stack pointer to, or the RSP register to just say, let's point, further out. And how do we get that number? We're just going to multiply the size of one integer. So, the size of one integer here, we know it's going to be 8 bytes. We just multiply that by the number of integers that we want. That's going to be 40. So we'll just decrease the stack pointer's value by 40. Because remember, again, when the stack grows vertically, it's actually growing downward in memory. So we're going to decrease by 40 there, at least in this drawing example. And that gives us a bunch of junk data, because there is always going to be some kind of a value sitting at every memory location in your computer. It's impossible that there is literally nothing at some memory location, unless you're trying to go beyond your RAM stick. But then the system will still acknowledge that you've done that, and it won't just give you back nothing if you try to read. So there's going to be junk data sitting on there, and then we'll loop through all those slots on the stack, and we'll just modify the data one by one so that we can control what it is instead of just printing whatever junk data we end up with. So really, we're just moving the stack pointer, just making room, and then just remembering where our array is. We could put another frame on top if we wanted to make just like one integer as a local variable. You just got to remember where it is. What is its offset? Okay, so I'm going to erase this, because we're going to do a lot more than 5 integers on the stack. But I just want you to understand what we're doing before we do it. Okay, so the next thing I'm going to grab is a move instruction, and I'm going to put it right here. So what is this? We're going to calculate how far to move the stack pointer, RSP. So the first thing I'm going to do is I'm going to use a temporary register. We don't need to preserve this in the push and pop because it's marked as temp, so we're not responsible for preserving it. So I'm going to say R10 is just going to be the number of integers that we want to create. If you recall, at the top of our program here, num integers is just 50. Okay, so then the next thing that I'm going to grab is, well, I'm not going to grab it, I'm going to straight multiply by integer size. So again, if you look at integer size, that's going to be 8 because we're using quad words for our integers. So we're really just going to take 50 times 8, whatever number that is. Is that 400? Tell me in the comments if that's right or wrong. And so you may or may not know, if you don't see more videos, see more textbooks, you may or may not know that the imul instruction just multiplies 2 numbers. If you use the 3 operand format, then the last 2 operands get multiplied and the result stored in the first operand. But if we use the 2 operand format like I've done here, then both of those operands get multiplied and then the result gets stored in the first operand. So basically at this point, R10 should hold the number of memory locations that we should move the stack pointer in order to make room for all those integers like I showed you a second ago. So then we're going to move the stack pointer. And maybe I'll leave a little comment here. Remember, the stack grows downward in memory. And so all I'm doing is subtracting the stack pointer. Remember the stack pointer register, it just holds a number, which is a memory location. So if you subtract some numbers from it, you're really having it go downward in memory. And that's what we want to do to, grow the stack for a local variable. So I'm going to say, well, I should also say that we're using the 2 operand version. So just like imul, if we had the 3 operand version, then the last 2 operands would have one subtracted from the other, and the result will be stored in the first one. But since I'm using the 2 operand version, basically it's taking RSP minus R10 and then storing it in RSP. So this instruction just says, let's move the stack pointer downward in memory enough times that we have room for all of our integers. Okay, no problem. Next thing that we're going to do is we're going to move R12. We're going to move into R12 the current value of RSP. Remember, is RSP. So let's see, downward in memory. Right. Plus, okay, so the first integer, it's up to you how you style this, because once we do the subtraction, then RSP is actually going to be pointing towards n integer. You could consider that to be the first integer or the last integer, because all we have is an array of integers. So you could say, RSP, wherever it's sitting when we're finished, we could say that's pointing to the first integer, or we could say it's pointing to the last integer. But if we decide to say that it is pointing to the, let's see. Yeah, if we're deciding that it points to the first integer, let me just do a little comment here. First integer, it just makes it a little bit easier for me to write our loop that iterates through integers. But just keep in mind, you could start by pointing to the one that RSP is pointing to, or you could start by pointing to the other one that was like the first one that you added onto the stack. You could call either one of those the first integer, as long as you remember where you started, so you can increase or decrease the memory location to get to the next integer. So I'm just going to do it in this style, but keep in mind, as long as the only thing that you modify and read is within that range, it's okay. So let's remember, where is RSP? So that's like the top of the stack. We're going to say R12 holds the stack pointer, so that we can use R12 as sort of a running pointer. I think that's the way I'm going to use it. Let me just double check my solution. Yeah, okay. So let's now do a calculation where we remember where the last integer is. So we know where the first integer, we're just going to call this the first integer. I'll put it in quotes just to remind you that this is just the style I happen to be using. So here we're going to say that the first integer is wherever RSP is pointing. And then in R13, we're going to remember where the other side of the array is. In this case, we're calling it the last integer. And pretty much it's just R12, which is where the first integer is. And then we add to it a memory location. So remember we said before that the stack grows downward in memory. So if we consider the top of the stack to be the first integer, then that means previous items, maybe I should draw this, are going to be increased memory locations. So that's kind of like the backwards of what you imagine a stack as doing, but it's kind of the way that I like it sometimes. So imagine just in a very simple stack, let's pretend that the stack has 1 byte values, which it doesn't, but let's pretend. If you, dude, I got to learn how to draw. I can't get that 5 right. Okay. I'm defeated. So let's pretend that that address on the thing sitting at the bottom of the stack is 5. So then that means the next address would be 4, right? But if we decided, let's say that let's do like a few more just to make it a little bit more interesting. Let's do a total of 5. So we'll say 4, 3, 2, 1. Maybe I should just add some numbers in front of those values so it doesn't feel like we're hitting 0. But so just pretend we have a memory location of 15. That's not going to be the case in real life. Pretend that we have 1 byte integers on the stack, which is not going to be the case. We're going to have quad words. But you can see the memory locations go downward, right? So then we'll see that the stack pointer is pointing to the topmost location. We have to remember that anything up here might exist in system RAM, but it's not considered valid data because we didn't make it part of the stack by growing the stack pointer. So that means these items, well, maybe I'll do a check instead of an X, because X looks bad. I'll do a check, and a check, and a check, and a check. These items are okay to use. So if I have RSP, or in this case, we just remembered where RSP was by storing R12. If we have that memory location 11 and we want to get an additional integer, like somewhere else, like the next integer, well, that would be, this one down here. We wouldn't go in the other direction. We wouldn't go, up. We would just go down in the stack, but down visually is actually growing upwards in memory, because remember, when we grow upwards visually, we're growing downward in memory. So, and you can see here too, if we're increasing 11 to 12, that means we're adding memory locations to get to the next integer that we have in the stack. So that's why here, my green is just like frustrating me. I still have to fix this. So that's why here we're adding a little formula instead of subtracting, because the RSP started there. We're saying that the top of the stack is the first integer, just so we can add in a more convenient, nice way. So what are we adding to it? We're just adding to it the number of integers minus 1. And then, so that's the number of slots that we'll jump over, and multiply that by the integer size. So if you imagine, if we had 10 integers, then 10 minus 1 is 9 slots. So if you imagine that 0 is the first integer, let's say the memory location again, then that means 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 minus 1 is 9. So if we added the number of integers minus 1 from the start, which we'll consider 0 here, that means it goes to the last integer directly. So that's just like a little math, because sometimes when you think of adding two numbers together, or taking the difference, or including the first number, or not including the first number, it's a little confusing, right? So keep in mind, for this particular calculation, we are adding to it the number of integers minus 1, so that will be sitting on the last integer rather than going past it. So start with the first integer's memory location, and then the number of integers minus 1, or size minus 1, times the integer size, because remember, every integer is going to be 8 bytes. And that will give us the memory location of the last integer in R13. And then I've said this in other videos, but basically You're only allowed to make these sorts of calculations in YASM when you have the calculation inside of brackets, but brackets will automatically dereference the value on the inside. It'll consider it as a pointer that needs to be dereferenced, but we don't want to dereference anything. We don't want to go to a memory location and take a value. The memory location is the value. So these dereferencing brackets, which are required for the formula, are kind of bad. So that's why we use the LEA instruction instead of the move instruction. If I put move there, it would definitely dereference the memory location and give me a value in R13. So R13 wouldn't actually be a pointer. It would just be the value of the junk data of the last integer. Keep that in mind. Okay. So where's RSP? So we got that. So now let's do a loop. I'm going to start off with a label called demo loop init. So for me personally, when I'm looping, I like to make my labels inside of my loops start with a prefix that matches the function. So it's like demo, and then everything else is going to be demo underscore something. So init loop init, I'm going to make a loop where I initialize the values of the array. So I'm calling this loop the init loop. And then the last part is just like, this is the initialization part of the loop. This is where we sort of like set up the initial values to loop. So we have R12 and 13 that point to the first and last integers. Now we're going to set up R14 and 15, where R14 is the running pointer. I think before I might have accidentally said that R13 is the running pointer. It just points to the last integer. But if you look back up at my comments, R14 is the running pointer to the current integer. What is a running pointer? It's just a pointer that runs. It's just a pointer that just keeps increasing so we can look at different data values. So I'm going to start it by looking at the first integer. So now R14 is pointing to the first integer, and then R15 is going to be the value that I want to put into that position in the array. So like the first integer, I want to put some kind of a starting value into it. You can put the number 0 or whatever you want. I just wanted to have a start value so that it sort of looks more like I'm putting data and less like I have a loop counter. So remember, the integer start value up here is just 7, so I'm just going to start at the number 7. And now I'm done initializing my loop. Then the next thing I'm going to add is the top of my loop. So you can imagine this as the top of a while loop where you start comparing some sort of an expression. Maybe I'll say expr to say that we're comparing some sort of an expression. And if that expression evaluates to true, the loop continues. If it evaluates to false, then the loop does not continue. Let's see. So I'm going to compare R14 with R13 inside of the top part. What is R14 and 13? Remember, R14 is the running pointer, and R13 is the last integer. So basically, I'm trying to figure out, am I looking at, or like, let's compare the running pointer with the pointer of the last integer. Then I'm going to say, if the running pointer has a greater memory location than the last integer, that means I've gone beyond the last integer. And again, the way I arrange the first and the last integers just makes it easier for me to think of them as having increasing memory locations. So I'm going to jump if the running pointer has already surpassed the last integer by saying, let's jump if it's greater than. So you can imagine maybe in the expression here, I should probably say while not R14 is greater than R13. Not a great expression, but it'll do. So that's what I'm implementing up there at the top. Let me just put that into my notes too, so that my notes match the video. Okay, so we are comparing, and then we're jumping to the end of the loop if we end up going beyond the last integer. So that label's not created yet. I'll create that in a moment, but pretty much that's a label that's just going to be below the loop, just to say like we're finished with the loop. Okay, now we're going to begin the loop body. I like to put comments here to help myself remember, oh, this is the part of the while loop that I'm currently inside of. Just makes things a little bit easier to understand. You put a block comment up top of every label or every chunk of instructions just to let you know the general idea. And then sometimes you put comments also on the right side to help you remember what each instruction is actually doing. So then what am I going to do here? Remember, R14 is the running pointer. If I deref R14, that means I want to move an actual value into that memory location rather than changing the memory location that R14 points to. So R15 is going to be the integer that we want to write into the array. So all I'm doing here is I'm saying, let's take that value 7, which is what it starts as, and just move it in to, the RAM stick at that memory location. So I'm setting the first integer to the R15's value, which is 7 right now. Then I'm going to increase R15. So that means every time we iterate the loop, we should see that the value increases. So the first integer should be 7, the second one should be 8, next one should be 9, and so forth. So just a simple loop where I'm just writing data into my array. So now that we've ended the loop body, let's write the bottom of the loop, which is just going to increase the running pointer and jump back up to the top. And this is not necessarily the only style for translating while loops. I'm just doing it. And, I'm going to make another video in the future where we talk about, for loops and while loops and all that stuff. But this video is just really about local variables on the stack. So I'm not going to go over all the different ways you can do it. Anyway, so R14 is the running pointer. So I'm going to just make the running pointer jump to the next integer, and we can do that by increasing its memory location by the size of one integer. Again, this is another benefit of the first and last pointers that I chose at the beginning. I can just increase to go to the next integer. So we're going to increase by 8 bytes to just go to the next integer. If you increase by 1 byte, you'll probably have a huge corrupted mess because you're messing with 8-byte integers, but you're only increasing by 1 byte. And then after we increase, we're just going to jump to the top of the loop. So notice how I have a jump statement here. It's going to go just to loop top. So now this part is basically just going to execute over and over and over again until we finally scan through all of the integers in our array. So that's the bottom of the loop. And then I'll make the label for the loop being done. It's not really going to do anything except just be done. And I don't know, depending on your style, maybe you can let it drop through if the loop's done rather than always jumping to the top. But I'm just going to say when we're done, we jump to the loop done label, and therefore there's no more looping of that initialization loop. Okay, so we got that done. Let me just run the program real fast to make sure that I haven't screwed it up. We actually should not see anything right now. Oh, what did I do? Must have done something naughty. Maybe if I finish this program, then everything will be okay. Oh my gosh. What did I even do? Well, I've got a working solution in the other window, so hopefully when I paste all the extra steps, everything will be fine. You never know. Subtract the stack pointer. Oh, did I forget to restore something at the very end? Print body. Move the base pointer into the RSP stack pointer. Oh, yeah, okay. That's definitely what you got. That's why it crashed. Okay, so remember I said you got to be very careful about the stack. This is a great lesson. So I did preserve the base pointer, but I didn't actually preserve the stack pointer. Notice how right here I subtracted from the stack pointer, but I did not restore the stack pointer anywhere. So that means I corrupted the stack for anyone that called me and also for my return address. So I'm kind of trying to copy paste my instructions from top to bottom, but I think I'm just going to copy paste something else to make sure that we can actually run this. So I'm going to copy paste into the Epilogue a restoration of the stack pointer. And that's why we saved the stack pointer in the base pointer, just to remember where it was when we originally started our function. So now on line 128, it should be restored and the program should work. Let me just double check here. Yeah, it worked. Okay. Nothing happened that we can see, but it did write values into the array. Now let's do another loop where we just print the array. So let's see, loop init done, loop init bottom and loop init done. Okay, so now there's like going to be another loop here. We're going to call this the print loop. And so the print loop is going to be kind of the same pattern. We're just going to loop through all the integers in the array, but instead of modifying them, we're just going to print them. So now, the first thing we'll do is we'll set R12, we'll store that inside of R14 in order to start the loop at the first integer. What was R14 again? That was the running pointer, remember? Let's see, where's that? Yeah, it was the running pointer. So now we're resetting the R14 running pointer to the very beginning of the array. And we know where the beginning is because we remembered that with R12. Then the next thing we'll do is we will set up the top of the loop and the body. So I'm just going to copy paste again this stuff right here. Right there. Okay. So the top of the loop, we're asking ourselves, we're going to compare. I'm not going to put all the extra while stuff that I put in the previous loop, because hopefully by now you understand loops a little bit better. But I'm just going to compare R14 to R13, and if we're beyond the last integer, because the running pointer R14 is beyond the memory location of R13, that means we're totally done. So we should jump if it's greater than. Now I feel bad. Let's put a comment in here on the top. Let's go. Basically that, if keep going as long as R14 is not greater than R13. So if it is, then just jump. Okay, so now we begin the body. And in the body, all I'm going to do is use R14, the running pointer, to print whatever value is sitting in that particular integer. So how do we do that? I'm just going to use the printf statement, or sorry, the printf function, which is provided by the C libraries. That's why we're doing, a modular or a hybrid program with multiple modules and C linking. So this is not a video about that, but just very quickly, there is a function called printf, which I can call. It takes multiple arguments, but the first two arguments that I can give it are the string that represents the formatting that I want to print. Like I could do like a regular string message. I could do tokens to format some data inside of them. And then the second argument is going to be the piece of data that I actually want to use. Let me see if I can just type that up for you real fast. So, the printf instruction, or sorry, this is not an instruction, this is a function in C. We would typically, give it some kind of string. The string should be null terminated, and it should have a new line at the very end of it to make sure that printf actually flushes. It won't flush if you don't have a new line, so the program will look really weird. But I guess it's more performant if you have a way to delay the flushing and you know that you can flush it later at the very end. But for now, I'm just going to flush every time. And then every argument after that is some sort of, data that we can print. So imagine we have a long, and we'll call it A, and we'll say that it has like some giant value. So that means we would give that long as the next argument, the RSI argument. And then for the string formatting, if you just kind of look up, this is what I'm using right here, %LU. So you can imagine instead of this string, it is this string right here. Whoops, too many quotes. It's just this string right here. And then instead of a 1013, that's the same thing as just doing a N, or if you want to be, more of a Windows person, /R/N, it's all good. And the zero is not needed because the string, if you put a string literal, it's automatically going to be null terminated, which means there's just a zero at the end of the string in memory. So this is basically what I'm doing. I'm making an integer. In the case of the assembly program, it's going to grab an integer from that position in the array that we're looking at, and it's going to give it as an argument, and then the first argument is going to say, let's just print this as unsigned long. So that's why I have that string here. Let me search for it and go down a little bit again. So I'm saying first argument is the format that I want to be printed. Second argument is the actual value. And then I'm going to make a call to printf. Why do I have this weird push and pop pair sitting around printf? So this is not a video about stack alignment in GCC, but basically the GCC libraries expect that your stack is aligned to, I think, 16 bytes. But since we use 8-byte integers, every single time we call a function, we're pushing a return address to the stack, which is 8 bytes. And then every time we do one single push or pop, we're modifying the alignment of the stack by 8 bytes. So if you think about it, when we're programming in assembly, for the most part, the stack is going in and out of alignment because every time we modify it by 8 bytes, it might line up with a 16-byte alignment or it might not. It's just kind of like oscillating, right? So when I first wrote this solution, I wasn't doing the push-pop pair, and this is what happened. Oh, actually, maybe, I guess I don't need to jump to the top right now. I don't need to finish the loop. Let's see if this prints just one number. Well, let me see if this prints one number. Certainly, and if it's an OK assembly program just to print one number. Is it going to work? Okay, we got to do the done symbol. Okay, so I'll show you in a minute why we need push and pop around that for stack alignment, but I guess I'll just finish the loop. So demo print loop done. So we just did print loop top, and that means we need the bottom and the done. So I'm just going to copy paste into the program here. I'll just say nada because we're not really doing anything. And then at the bottom, that's the epilogue. That's separate from the other label. So basically now, let me finish describing the loop because we already know the loops, but I'll just say it. At the bottom of the loop, we do the same thing that we did with the initialization loop. We just increase the running pointer. We move it along to the next integer, and then we jump to the top of the loop. That's it. And then the done label, we don't really do anything. We're just letting execution drop through down to that point so that the loop doesn't continue. So now we should be able to run the program. Don't get excited. Oh, actually, you know what? Get excited. I was going to say don't get excited because it was going to totally work now, but now I think we can just say that it's going to crash. So if I run it, notice how there's a Segfault. So the GCC libraries, many functions expect your stack to be aligned to 16 bytes. So if you see mysterious crashes and you are absolutely sure that you're not ruining the stack pointer or ruining something else, you're doing everything correctly, but the program still crashes, it might be stack alignment. So one way to get around stack alignment is just to move the stack pointer. Like at the top here, we could have said, oh, we've got 1, 2, 3, 4, 5. We've got 5 pushes. And then here we're moving the stack by, I don't know, how many other addresses. The stack might be out of alignment somehow. So we could add an extra push up here and then add a corresponding pop down at the bottom. Like we could easily do this. Let me just show you real fast. We could push R15 twice. For no reason, I acknowledge, and then at the bottom we pop R15 twice. That would change the alignment because that's one more 8-byte push. But in my case, and actually that would be a little bit smarter because you will, if you have our loop where it's constantly calling on printf, this is a lot of hits to memory, right? This is like 100 hits to memory because every single time we do a push pop pair around a call to printf, we're like touching memory. Whereas if I did it at the beginning and the end, maybe I should just do it this way. I want to do it both ways so you understand, but it's more efficient, I think, if we do it this way. Anyway, so we'll do pop twice at the bottom and then push twice at the top. And so then we don't really need to surround it with a push pop pair. I think, I haven't tested this. We'll hope now that the stack is in alignment at all times in our function so that it doesn't crash. Yeah, so now see how the program works. So I'm going to do it the other way now, which is the less efficient way, because here we just have one extra push-pop pair. But if we do it the other way, it'll still work, but we'll be hitting memory much more often. So I'm just going to do it this way. Just to show you, you can surround any call, because sometimes in your programs, you might have the stack modified throughout the function many different times. So it wouldn't make too much sense for you to add an extra push-pop pair in the Prologue and Epilogue, because that might not solve it for all of your calls to all of your C library functions. So in that case, where you can't really predict the stack well enough, you can just surround your call with the push pop pair. It hits memory more, but it'll work. So this is basically, you can imagine, by the time we get to line 139, the stack is out of alignment. So I just do a push that puts it into alignment. And then after the call comes back, I just pop it so it's back out of alignment again, but I don't have extra erroneous data sitting on the stack. Because if I only had push and not pop, then it's going to push it more and more out of alignment. It's going to push it in and out and in and out, but it's going to add a bunch of junk data to the stack that I'll never recover from. Or actually, I guess I will recover at the very end when I restore the stack pointer, but it's pointless. It's going to consume too much memory. What if I was what if I was writing like a billion or like a million items as like on the stack, right? So like a billion iterations of the loop would probably be a bad idea to start adding onto the stack. We'll probably end up stack overflowing, probably with far less than a billion items. So anyway, I'm going to surround the call with the push pop pair. And then at the bottom, we just do the same thing, increase the integer and then go to the top. And so now, you already can see it on the screen, but basically the program works. And what it does is it starts off printing, well, it starts off initializing the array, but then the thing that we can see starts off printing the first integer, and then the next iteration of the loop prints the second integer, and the third, and the fourth, and so forth, until we get all the way down. And just to prove to you, maybe we can increase it by 2 instead of 1 each time. I'll just modify that real quick. We'll do, where's the bottom of the loop? Oh no, that's the print loop. Let's do the init loop. Init loop bottom. Oh, right there, when we're in the body. So I'm just going to increase R15 twice, just to show you, we can kind of control what's going inside of the local array. So see how it goes from 7 to 9 to 11 instead of 7, 8, 9. So I'm going to take that out and then just show you that we can control how many integers we have in our local array with just the number of integers. So I'm going to change the 50 to a 5 and run it again, and you can see, what the dang did I do? Number of integers is 5, and then it was 50. Did I put the stack out of alignment? No, I have a push pop pair there. Number 50 is not hard-coded anywhere. I wonder if I just messed something up. Yeah, it works when it's there. Oh, I have a bug that I can debug. That's nice. I guess the bug debugging is not for this video. I wonder if some other value would work for that. There's a number of things that could be the problem. It could be like stack alignment somehow. It could also be, let's see, am I making any calls here inside of my function demo? I'm saying sub and LEA, and then start, and then jump, and then increase, and then jump, and then RDI. Not really doing anything else, so I don't think it's stack alignment. I must have miscalculated somewhere somehow for changing that. All right, well, if I figured it out, then I will release another video, but basically this is the idea. 100 works, 50 works. What about 99? Would that work? Segfault's on 99, and then 98. 98 works, so like every 2 seems to work. But that is 2 quad words, or 16. Oh, right? So like 100 integers, if we assume that that's in alignment, then 99 would be 8 bytes less that we're moving the stack by. Notice how it segfaults, right? Okay. And then 98, notice how it is okay. And then 97, it's going to segfault again. Watch. This is a great stack alignment video, I guess. 96, it won't segfault, so it's going in and out of alignment. I think I figured it out. So if we use the number 100, it's in alignment. Sorry, it's out of alignment if we use the number 100. The program works because the number 100 throws it out of alignment, but then we have this push-pop pair here around the call to printf, which puts it back in alignment. So if I change the number of integers, I'm actually changing the number of memory locations that I modify the stack pointer. So I have to do it by 2s. If I wanted to do 99 here, then that means the stack is in alignment by the time I call, by the time I'm getting ready to call printf, which means the push pop pair around it throws the stack out of alignment. So just watch here, I'll prove it. Okay, so it's segfaults. If I comment that out, now it won't throw it out of alignment. Okay, should have known that before I recorded the video. It's fun to guess sometimes though. I get a little nervous. Oh no, my program broke on camera. Can I debug it live? Well, I guess I can, but kind of slowly. Anyway, so I think we've gone over every single part that I wanted to show you. We know how to create a local array on the stack. And therefore, you also know how to create like any other data type on the stack if you want. You want to create a 64-bit integer? Just move it by 8 bytes instead of moving it by 8 times however many integers we were doing in this video. You want to, I don't know, put a character on the stack? You can do that if you really, really want to. Just, move it by 1 memory location instead of 8 memory locations, or, 1 byte instead of 8 bytes. You want to store a short, a 2-byte integer, we'll just move it by 2 bytes instead of 8 bytes, right? So you can do this as many times as you want. If you want to have several local variables, just move it 1 time for every local variable. Same thing for accessing. You just have to remember where everything is. Either remember what is the offset of the first variable, local variable, and then the offset of the second local variable. You can store those in globals or store those in registers if you can. You just got to remember somehow where everything starts, but it's all sitting on the stack if it's a local variable. Okay, I guess that's everything that I really have to say. I hope you enjoyed this video. I hope you learned a little bit of stuff and had a little bit of fun. I'll see you in the next video. Have a good one. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.